Hello, boys and girls, ladies and gentlemen, fellow Homo sapiens, welcome to today. A quick talk on work and kinetic energy and the work energy theorem. Okay, to start with, we know that work is defined as force times distance times the cosine of the angle between them, because the force needs to be applied in the same direction, the same parallel as the distance covered. Okay? Let's, for our sake, assume this is going to be correct. It's going to be 0 or 180 exactly. So we're going to get rid of that term. Then we look at the fact that force, by the second law, is mass times acceleration. And distance, couldn't we say distance is simply x sub f minus x sub I? Don't we call that delta x? To go back to some terminology we've already had. So then this would be max here. If we do that, we can go back and look at a formula we had, that v sub f squared equals v sub I squared plus 2a delta x. Oddly enough, 2a delta x, we have a delta x here. Subtract this, v sub f squared minus v sub I squared must equal 2a delta x. Divide by 2. And what we get is v sub f squared minus v sub I squared times 1/2 must equal a delta x. Substituting in then, don't I get that my net work then must equal m times 1/2 times v sub f squared minus v sub I squared? Distributing that out, taking a look at this as 1/2 m v sub f squared minus 1/2 m v sub I squared, where this is the kinetic energy final, this is the kinetic energy initial. So we're saying that the net work done on an object is simply the difference in the kinetic energy. Kinetic energy, Ke, not to be confused with temperature, kinetic energy is the energy an object has because it is moving. Our definition, kinetic energy is very simply 1/2 mv squared. As we look at that, we know then, we could say then, that this is very simply equal to delta Ke. If this is the kinetic energy final, and this is the kinetic energy initial, that's simply the definition of the change in kinetic energy. So for an object that's moving, the net work done on the object deals with its change in kinetic energy. So when I take a look at that, I have again, that was derived in the textbook and just wanted to go over it with you. We have then that if the net work equals delta Ke, that is equal to 1/2 m v sub f squared minus 1/2 m v sub I squared. Again, delta is always final minus initial. Delta x is always the final minus the initial x. Okay, we have that. Well, isn't this simply force times distance? Just want to make sure that I know where I'm going here. To solve for any of these things, if I want to solve for the distance covered, one more step. We have a mass and an acceleration here, times d equals 1/2 m v sub f squared minus 1/2 m v sub I squared. Okay, I know in the example problem they give you on page 167, they solve for d, but realize in that particular problem, when they solve for d, it was the fact that the final velocity was 0. If we wanted to solve for d now, d would simply equal 1/2 m v sub f squared minus 1/2 m v sub I squared all over ma. Well, notice, m is going to cancel out, It's a factor of both of these terms, so I could pull it out. So this would equal 1/2 v sub f squared minus v sub I squared over a. One of these may be 0. Both of them cannot be 0. If we're looking at the net work done and we say it was at rest and ended at rest, we're missing the question. Net work done. We're saying that if it started from rest, great. Then the final velocity is what we have to look for. If it ended at rest, then we had to look at the initial velocity. If it simply changed speed, we need them both. So don't let that confuse you. Okay? This force might be a few other things. It could have been the frictional force over the distance applied, those kind of things, but this is what we're looking at. So if I was solving for D, this is how I would do it. Don't forget, this is what you were given. This is the definition. Okay, I will try to do a couple of these problems in a bit here to give you an example, but take a look at this. Of course, we could have the cosine of the angle in here now. We only ignored it for that example that we were doing. So you do the cosine of the angle, so you have the force times the cosine of the angle in between them. And I hope you're doing well. So drive fast, take chances, doing appropriate things with people your own age. Be safe. Miss you guys.